So we have three speakers this session, and I'm very happy to introduce Bob Paré, who will kick off the session telling us some things about double categories.
Thank you, Bryce. I'm really honored to be able to kick off what looks like a very interesting workshop. And thanks to you and Tim for a very good job in organizing it. Okay, so I'm just going to jump in and start off with the definition. Whoops. Ehresmann introduced in the early 60s double categories and two categories, just in passing. And they were extensively developed together with André Ehresmann through the 70s. Unfortunately, their work was largely ignored, perhaps because it was very much ahead of its time, and also because of maybe difficult notation with rigid adherence to sort of the arrows only approach to categories. Whatever, I mean, there were also other things going on, toposis and so on, but definitely the time for double categories has come. So a double category is simply a category object in cat. Okay, and you can see here you have two categories, A0 and A1, and you take the pullback, and then you have, well, you have functors, D0, D1, you take their pullback, and then you give two other functors, and you require that it be associative and unitary. And a double functor is simply it's a morphism of category objects. So it's a functor from A0 to B0 and a functor from A1 to B1. Now, this is a very precise and concise definition, but it doesn't tell us very much. So let's dig a little bit deeper here. What you have is A1 here is the object of morphisms. Okay, so an object in here should be a kind of morphism, but A0 also has morphisms. So you have internal and external morphisms, two different kinds of morphisms going on. So just to set notation here, an object of A0 will be called an object of the double category A. And a morphism of A0 are going to be called horizontal arrows, and I'm going to write them as much as possible horizontally and just an ordinary arrow like this. Whereas the objects of A1, we're going to call them vertical arrows and denote them as much as possible vertically and decorate them with a little dot here, just in case sometimes we can't put everything horizontal and vertical. And finally, the morphisms in here are double cells. And now the F's, of course, compose, I mean, they come from the category A, so they compose to give us a category. But the alphas, who are morphisms in here, also compose to give us a category. And the vertical arrows compose, and so do the cells compose, and you get associativity here in this definition. You get a category, you get another category, and you get associativity horizontally and associativity and vertically, and you get interchange. Okay, so I mean this is I'm going fast. I think that most people know this, but I'm just mentioning this now. This doesn't really do justice, you know, to the richness of the subject. So my take on double categories is this: is that a double category is a category with two kinds of morphisms suitably linked. Okay, so it doesn't quite make sense because you know, a category has morphisms. Okay, so but I think it gives the idea of what it is. So whenever you have two different kinds of morphisms going on, either you have two different kinds of objects, two different categories, or else maybe you have a double category. Okay, so this is the way I think of double categories. So here's an example. Maybe when you're learning category theory, the first time you see a category that has two different kinds of morphisms is when you take the opposite of a category. So in the opposite of a category, well, you know what it is. And you have, as I say, two different kinds of morphism going on there. So you can make this into a double category, which I'll explain this notation in a minute here. So the horizontal arrows are simply the morphisms of A, but the vertical arrows are the morphisms of A opposite. And so a vertical arrow from A to C in this double category is morphism going backwards from C to A in A. And here there's at most one cell, and there's one precisely when this square here commutes. Okay, so I denote it this way. Square A, that's the double category of squares, and co is the vertical dual. Okay, so whenever I taught category theory, students had trouble with opposite. I never understood completely what their problem was. But now that I do double categories and there are a whole bunch of different opposites, I see that it can be quite confusing. But they would say to me, well, oh, you're taking the inverse of the morphism. And I said, no. And maybe the morphisms don't have inverses. Well, you take the inverse relation. And I kept telling him, no, it's just a formal thing. Okay, you just define it that way. Okay, so eventually they caught on. But let's look at student duality here. Okay, so suppose that we have a regular category. So I want to make relations now into a double category, and what you need is some conditions on a category to make relations work well. And the correct conditions are that it be a regular category. So let's say it has finite limits and it has co-equalizers of kernel pairs, and that the regular epis are stable under pullback. So if you have that sort of category, you can construct a double category of relations where the objects are the same as the objects of A. The horizontal arrows are just the morphisms of A, but a vertical arrow now is a relation from A to B. So a relation from A to B is a subobject of A cross B, like this here. And there's exactly one cell here, if and only if the F cross G restricts to the relation. Okay, so if you're thinking in sets, what this means, if you take an element little a in here and another one little b, then A is related to B by R, implies that F of A is related to G of B by S. So there's a cell here if and only if there's only one cell, okay, or there's none. And then now we can take this category built out of opposites and embed it into here. Okay, so you have a double functor, which is the identity on objects and horizontal arrows, and it's faithful on vertical arrows and full and faithful on cells. So the students weren't really that wrong in thinking that you can think of it as being taking the inverse relation, although it's not an inverse. Okay. Now, the embedding here takes it's the identity on objects, and what it does is it takes a morphism from A to B in this double category. That's a morphism in A going from B to A, and then you take the reverse of its graph. Okay, I call this V double star. Okay. Now, is there a black thing at the top of your screen or not? It's just my screen. Okay, good. You might think that functions are relations, or so typically set theorists say that a function is a relation such that such and such, and category theorists take the opposite point of view, is that a relation is a kind of function. Well, it's a sub-object. Okay, so maybe it's best just to keep them separate and see how they're related. And they're related in the following way. Every morphism has associated to it two different relations, its graph and the opposite of its graph. And you can define this in any double category. And so it's called companion. Okay, so if you have a morphism from A to B, a horizontal morphism and a vertical morphism from A to B as well, then you say that V here is a companion of F. If you have two cells like this, binding cells, or Ronnie Brown calls them connections, such that when you compose these two guys horizontally, you get a vertical identity, and when you compose them vertically, you get a horizontal identity. So we're thinking now that V is the same or isomorphic, in some sense, to F. Okay. Now, companions may or may not exist in any double category, but if F has a companion, then it's unique up to isomorphism. The identity always has a companion, namely the vertical identity, and identities compose. Okay, so now the vertical dual of this is the notion of companionship, conjoint. Sorry, we are just talking about companionship there. So the notion of conjoint. So now you start with a horizontal arrow from A to B, and you're thinking you have a vertical arrow from B to A. And you say that this vertical arrow W is conjoint to F if you have cells like this, alpha and beta conjunctions, such that when you compose them horizontally, you get a vertical identity, and compose them vertically, you get a horizontal identity. Okay, so it's almost the same as the other. Well, in fact, it's the dual. Okay, so this looks the same, and this one here, the alpha and beta are switched around. And so, of course, they're still unique up to ISO when they exist, and so on. So what we're thinking is that W like this is sort of adjoint to F, even though they're different kinds of morphisms, they're sort of adjoints. In fact, we can define adjoints in a double category. I'm just going to concentrate on the vertical arrows, but you can do it for horizontal arrows too. So two vertical arrows, V and W, are adjoint. So W is left adjoint to V if you have a unit and a co-unit. Okay, and this is what the triangle identities look like when you write them out in terms of double categories. Okay, so this is the eta epsilon is identity, and it's also eta epsilon identity, but they're sort of padded on the left and the right here. Okay, so this is just the notion of a junction in a two category, for example. And now adjoints, companions, and conjoints are all related together. So in fact, if the F lower star, the companion, is always left adjoint to F upper star, the conjoint, when they exist. Okay, so this is the upper star and lower star is not the same as for toposes. So if you have any two of these, then you have the third. Okay, so as I said, a companion is left adjoint to a conjoint, but if you have a companion and has a left adjoint, then it's a conjoint, and so on. Okay, so I said, I don't know if I said that right, but it's written down here. Any two of these conditions implies the third. In REL, every F has a companion. I already mentioned that. That's sort of the motivating example for it. And it also, every F has a conjoint. And furthermore, every adjoint pair is of this form. Okay, so we say now that REL A is Cauchy. So this is Cauchy in the sense of Cauchy complete for V categories that you probably know about. Okay. Now, another notion that you can get in a double category is that of a tabulator. So these were inspired by Freud's tabulations. So his idea was you have a relation, then you can tabulate all of its values. And he, in a book with Shedroff, defined tabulations equationally. They had lots of structure going on. They weren't doing two categories or double categories or anything. It was all one category theory with equations and so on. And so you can define this in any double category, may or may not exist. And so a tabulator, I mean, is a universal cell like this. So what does a cell like this mean? I mean, you stick the identity in there and it's a cell like this. And so universal, so this is the tabulator, T of V. It's universal if for every C like this, there exists a unique X mapping into it, such that when you compose X with tau, you get XC again. Okay, so tabulators, as I said, may or may not exist. They're effective if the T1 here has a companion and T0 has a conjoint. And when you compose the conjoint with the companion, you get V again. Okay, so that's sort of the idea of what you're trying to do with tabulators. You're trying to write a vertical arrow in terms of horizontal arrows and companions and conjoints. Okay, good. So rel A, whoops, rel A has indeed effective tabulators. I mean, it's not surprising. It's almost tautological, but I mean, you have to do a little bit of work to get it. But in Barr's paper on relational algebras from a long time ago, he used this a lot. Okay, every relation is a composite of sort of the inverse, he said, of a function followed by the function. Okay, so now I would say the conjoint of R0 followed by the companion of R1. Okay, so now let's look at what double functors are going from rel A to rel B. So a double functor from rel A to rel B. So first of all, rel A has as its horizontal structure is just A, okay, and rel B, its horizontal structure is B. So if you have a double functor, right away you get a functor from A to B. And now double functors preserve conjoints and companions, and since every relation is a composite of these two, the double functor will be determined once you know what that functor is. But it might not give you a double functor, give you something laxer a bit. But to get a double functor, as we've defined it, all you need is that it preserves quasi-pullbacks. So a quasi-pullback is a commutative square, here this Q, then A, B, and C, such that when you look at the comparison map with the actual pullback, it's a regular epi. Okay, so these are a little bit tricky, but anyways, okay. So for example, preserving pullbacks doesn't mean that it preserves quasi-pullbacks. Okay, so preserving pullbacks plus preserving regular epis would indeed mean that it preserves these. But so anyways, that's the condition for double functor. Now, the category of double categories, so the double category, double functors, is Cartesian closed. So this is a general fact. If you take category objects in any category, and in a Cartesian closed category with pullbacks, then the category of category objects is going to be Cartesian closed. So what that means then is that the functors from A to B have horizontal and vertical morphisms between them and double cells as well. Okay, so you don't have to sort of invent these. They're given to you by Cartesian closeness. You have horizontal transformation. So it looks a lot like a natural transformation, a horizontal transformation. For each object A, you give a horizontal arrow, and for each vertical arrow, you give a cell, T of V here. And these have to satisfy two conditions. So it's horizontally natural. So first of all, on the arrows here, it's just an ordinary natural transformation, but it's also natural on the cells. You have this condition here. And it's vertically functorial. So if you have two V's that compose, then you look at the cell corresponding to it. And if you compose those, then you get the cell corresponding to the composite. And then there's a condition here for the identity as well. Okay, so these are horizontal transformations. Vertical transformations is just a transpose notion. So transpose is the kind of duality where you switch horizontal and vertical. And so it's for each object you give a vertical arrow, and for each horizontal arrow you give a cell, and it's vertically natural and horizontally functorial. And then double cells are more or less what you think it is. You have to sort of write out what the conditions are, but so for each object A, you give a cell, and there are two conditions, that it has to be horizontally and vertically natural. Okay, so that's this is what this is. So now let's look at what these are in terms of rel. Okay, so if you have two quasi-pullback preserving functors, then they extend to double functors between the double categories of relations. And the horizontal transformations are just natural transformations. Okay, so they correspond bijectively to natural transformations from F to G. But the vertical transformations are a little bit different. They're relations. So it's a subfunctor of F cross G. But in this category here of quasi-pullback preserving functors and quasi-Cartesian natural transformations. So it's natural transformations where the cells are quasi-pullbacks. Okay, so I think that this category here is a regular category because the relations work well, but I haven't actually checked it. As I said, you know, quasi-pullbacks are a little bit tricky, and so you have to sort of, I mean, you're thinking of them as being pullbacks, but some of the things that pullbacks do, they don't, and so on. Okay, so I think this is true, but I don't know. Now, maybe in a course in category theory, the place where you first meet a category that has two rather different kinds of morphism is for Kleisli categories. Given a monad on A, you get a Kleisli double category. So the morphisms, horizontal morphisms are just the morphisms of A, but the vertical morphisms are Kleisli morphisms. So a morphism from A to C in this double category here is a morphism in A from A into T of C. And there's a unique cell here if and only if this square commutes. Now, every horizontal arrow has a companion. This is just the usual way that you embed A into the category of, into the Kleisli category. So you simply compose with the unit of the adjunction. Okay, so you have a morphism from A to B, and then you compose it with A to B, and you get something from A into T of B, and that's the F lower star here. So this is companion, and conjoints don't exist very often. In fact, F has a conjoint if and only if T of F is invertible. Okay, so now maybe somewhat surprisingly, it has tabulators, or at least under reasonable conditions. And so it has tabulator if and only if it has pullbacks along the eta A's. Okay, so this is pretty easy. A cell like this that you're trying to find a universal one of corresponds to a commutative square like this here. And using naturality of eta, you can convert that into this commutative square. And now you see that the universal commutative square like that is the pullback of phi with eta b. But the tabulators aren't effective, partly because you don't have conjoints. And so I don't know if this is any good or not, but it's something to keep in mind. Now, what do double functors between the Kleisli categories look like? Well, a double functor from the Kleisli on the monad T and the Kleisli on the monad S correspond to monad morphisms from T to S. So monads are monoids, and so you would think that monad morphisms are monoid homomorphisms, but we're thinking now of monads on possibly different categories, A and B, and so you have to sort of switch from A to B, sort of. And so a morphism from T to S it's a functor from the A that T lives on into B, and a natural transformation now going from psi T to S psi, and it preserves units in this sense, and it preserves multiplication in this sense here. Okay, so this is standard notion of morphism of monads. And now, what about transformations? So in the original paper, formal theory of monads, Street defined morphisms of monads, but also two cells. So a two cell from a morphism phi into psi is a natural transformation from phi to psi, which commutes with the structure arrows here like this. 20 years later, Lack and Street published Formal Theory of Monads 2, in which they introduced a new two category of monads in order to get to show that it's the free two category generated by taking Kleisli construction, and so I call these, let's say, Lack Street two cell. So a Lack Street two cell is not anymore something from phi to psi, but from phi to S of psi. So it's a kind of Kleisli kind of morphism, and it satisfies this condition here. Okay, so right, okay. So the double category take on this is that if you have two monad morphisms, which give us double functors now between the Kleisli double categories, then the horizontal transformations correspond to the Street two cells, and the vertical ones correspond to the Lack Street two cells. So that's nice that you actually get these two things which came up independently and somehow seemed unrelated, coming out just as horizontal and vertical morphisms of double functors. Now, actually, the morphism that I defined for monads, there are two different kinds of morphisms of monads. So there's the lax one, and the other one was oplax. Okay, so a lax morphism of monads is a functor again from between the categories, but now the transformation is going in the other direction. Okay, so and it satisfies again that it preserves units and multiplication. Okay, so the psi was oplax. Now the lax ones are good for Eilenberg-Moore. Okay, so a lax functor, that's the phi that I defined before, corresponds to liftings of the functor phi to the Eilenberg-Moore algebras, whereas the oplax ones, the psi, correspond to extensions to the Kleisli categories of the phi. Okay, so one works well for Eilenberg-Moore and one works well for Kleisli. But here, okay, now we have a category of monads that has two different kinds of morphisms, so they should fit into a double category. And that is the case. So now we have this double category monad. And so the objects here are monads so a category equipped with a monad. And the horizontal arrows are the lax guys, and the vertical arrows are the uplax guys. And the cell is a natural transformation. The natural transformation is going down like this. Okay, so it's going from psi prime phi into theta psi. Okay, it's interesting because it has to go that way. If you try the other way, you get a diagram that nothing commutes, nothing composes, so it doesn't commute. So it's a morphism like this, such that this hexagon commutes. Now, commutativity of hexagons might ring some danger bells for you, especially if you were marked as a young category theorist and discovered that dinatural transformations didn't compose at all. Okay, and so. But it could mean something else. It could mean that it's really part of a commutative cube, and that's what it is. In this case here, is that the condition is that you have a commutative cube. So you have these alpha, and you have these structure maps, and this cube commutes. And once you look at it that way, you see why they would compose. Okay, so the hexagons don't seem to want to compose, but the cubes, if you have two different ones, you can place them horizontally and vertically, and there's no problem. Okay, good. So in this double category now, a lax guy phi has a companion if and only if the structure map psi is an iso. So that means that it's lax and it's oplax, but not just lax and oplax, it's lax and oplax. The structure maps are inverse to each other. It has a conjoint if and only if phi has a left adjoint. So if you have a lax guy which has a left adjoint, then the left adjoint is automatically oplax, and it's a conjoint. And maybe surprisingly, this double category has tabulators and they're effective. So what is this tabulator? If you have here an oplax morphism, so a vertical morphism from T to S, then the tabulator is given by this comma category. So the comma category psi arrow B has as objects A, and then maps a psi A to B, and yes, that's what the comma category is. And then it's equipped with a monad. So the monad simply applies the T to A and the S to B. Okay, so T to A and then S to B. You apply S to little b, but it's not going in the right direction. But now you use this colaxity for psi to put it in there. So all of this works. This gives you a category with a monad. The projections they actually preserve the monad on the nose, as you can see. So they're both they both have companions, but P1 actually has a left adjoint. So the left adjoint takes A here to the object A, psi of A, and then equality A. Okay, so you see the B here becomes a psi of A, and so if you go by the adjoint there, you get psi back again. Okay, so this I think is a little bit surprising. Now, just for a change, let's look at the Eilenberg-Moore construction. So as I said, if you have a lax morphism, then it gives you a functor from the Eilenberg-Moore algebras to the Eilenberg-Moore algebras over the other monad. Okay, but what about the Oplax guys? So I said that they give you math between the Kleisleys, but I would like to see what they do for the Eilenberg Moore guys. And so what they do is you get a profunctor. So you get a profunctor from the Eilenberg Moore on T into Eilenberg Moore on S. Okay, and for me, a profunctor goes from the opposite of this category across this category into sets. Okay, so I don't know, 75% of people use the opposite convention, but anyways, this one works for me, and it's what I'm using here. And so the profunctor, then an element in here is simply a heteromorphism, if you like, is a map from psi of A into B, and you're trying to say that it's a homomorphism, but of course it doesn't make sense because if you try to write it down, it doesn't. But if you stick in this oplaxity here, then it does. So that's what an element is there, and that's the kind of thing that an oplax morphism of monads gives you on the Eilenberg Moore categories. So it also extends to these cells alpha. Okay, so those are the guys that had a hexagon associated with them, and you get here a morphism. It's a natural transformation between this profunctor and this guy in which you've substituted this in. Okay, and so what you're getting now is a kind of double functor from this double category monad into cat. But what is this cat? So the cat has objects are small categories. The morphisms are functors. Horizontal morphisms are functors. The vertical morphisms are profunctors, and the cells are natural transformations from P into Q, F, G. Okay, this should remind you of the relations example that we had at the beginning. Now, composition of profunctors, of course, uses coends, and so it's not really associative on the nose. It's only associative up to coherent isomorphism. So what we're getting now is a weak double category. So possibly when I defined double category for you, you were thinking, oh, those vertical arrows should not be composing to give you a category. Well, now we're changing our story a little bit here. Cat is a weak double category, and in fact, EM is not a weak double functor, it's a lax double functor. Okay, so let's go back to our definition of double category here. So we had double category, these two categories, these functors, and so on. And so and now we're going to, instead of having associativity, we stick in an associativity isomorphism. There are also isomorphisms for the unit, the left and right unit, and these satisfy the usual conditions. Okay, so this is a weak category object in now. Cat is a two category, okay? And so we can talk about weak category objects there. And lax double functors. So now you again have two functors, F0 and F1, and they commute with the D0 and D1 and P, whoops, typo here, P1 and P2. But they don't commute with the identity, and this, you have comparison cells satisfying conditions, which I won't go into. And so that's basically it here. And this is where actually the story begins now, rather. So we've gone full circle, and thank you.
Thank you very much.
Yeah.
People are giving some silent applause in the background. Everyone should be able to unmute now. So I guess this is the chance to ask any questions.
Hi, I have a question. So you've shown this functor, double functor from monad to cat, My question is this lax or unitary lax? So does it preserve identities or is it also lax on identities?
I don't know offhand. I suspect that it's unitary lax. Yes, I'd have to check. I mean, that's what I would guess. Actually, almost all lax functors are unitary lax. Okay, and so right. I don't know offhand. Okay.
Yeah, no problem. Thank you.
Thank you.
If there's any other questions, feel free to raise your hand or just jump in.
Hi there, can you hear me?
Yes.
Yes.
Hey, Bob, how are you, it's Martin? Hey, I was wondering about what you said before about being Cauchy complete, way back in the relations.
Yes.
I'm not really seeing the link with absolute limits or idempotent splitting. Do you want to kind of tell us a bit more about it?
Okay.
If you want to.
Yes. So, this is from Levier's original paper on metric spaces. He's viewing metric spaces as enriched categories, enriched in a monoidal category, which is made up of the real numbers, the positive real numbers. And he showed there that profunctors are representable precisely when adjoint profunctors. So a pair. So for profunctors, if you have an adjoint pair of profunctors, it doesn't necessarily come from a functor. Okay, it comes from a functor only if the codomain category has split idempotence. And so, this is yes. This is where this is coming from. Okay, so it's the split idempotents are in some sense an accident. Well, in another sense, maybe not. But I mean, if you're looking, for example, at additive profunctors, then the Cauchy completion of an additive category is not just splitting the idempotents, but you have to take direct sums as well. Okay, so I mean these are the absolute limits that you're referring to. Okay, so it's I don't know if maybe it's not very coherent, but it's certainly pretty far from anything that Cauchy might have done. Let me put it that way.
Thank you, Bob.
Yeah.
Go
Can I
ahead.
jump in? Hi, Bob. Here is Marek speaking. And, I wanted to ask about this double category of monads with lax and oplax morphisms. I liked it very much. And, once I had such an observation that, that essentially lax structures at the two level, right? Algebraic like structure commute with oplax structures. For example, they do not commute with themselves. Right. Do you have any double categorical explanation of this fact in a bit more general context than just monads, right? I mean, just like monoidal categories or braided monoidal,
Yes. So actually, Mike Schulman and Linda Wester, I think wrote. No, they did something else. But Mike Schulman certainly so at one point, I had realized that if you take a monad and you look at the lax algebras and the op-lax algebras on it, you can make it into a double category. Okay, so this very general sort of thing. And Mike Schulman was visiting here, and I told him this, and he said, "Oh yes," he said, "This is a general construction where you take I guess a monad. I'm not sure exactly what it is that he said, and you build a triple category out of it, where you have the strict morphisms in one direction and the lax in the other, and the op-lax in the other direction, and this has a universal property." And that he had never written it up because he didn't have sort of the machinery to express sort of the universal property. And I think that this is what the paper that he did with Linda actually accomplished. And maybe he has in there, I forget now, that. So I mean, so this is a very general sort of phenomenon that, as you say, I mean, the lax don't commute with each other, but they somehow commute with op-lax. Okay, so that's, I mean, this keeps coming up over and over again, and sort of the germ of this idea is in this category square up. Okay, where you take the opposite, and so somehow you have. In that very simple case, you have morphisms and morphisms in the opposite category, which normally we think of as being sort of just two different kinds of things far away, but they're actually related, and then you can just say what it means. And then somehow building on that, everything sort of cascades, and it gives you all sorts of lax and op-lax things forming into a double category. I don't know, Marek, if that answers your question, but it's
well, to some extent, yes, but
yes.
So there is something to think about, definitely.
Yes.
Thank you very much.
Okay, sure.
Go ahead.
Hello,
Hi.
thank you for this nice talk. I
Thank
wanted
you.
to ask, so now you said this is a general construction about this double category with lax and op-lax morphisms of monads. Could you give just any reference where it is written out?
So I think in this paper by Mike Schulman and Linda Wester, I think it's in there. I'm not sure, but I think so. I think, and yeah.
So I don't know if you now presented this as a, how to say, like presentation of something that existed, or is it your recent work? So that's why I asked.
Right. Well, it's mostly stuff that exists. You know, it's mostly expository talk, but
Okay.
so sort of just following the idea of having if two kinds of morphisms appear sort of naturally in a context, you should put them into a double category and study it that way. And so just following my nose, you come to this here. Okay, so I mean, you can do the same thing with monoidal categories, and you have monoidal functors and co-monoidal functors, and again you get a nice double category there, and it has nice double category properties and so on. You know, it's it is a or as I said, if you take a two monad and you can look at lax algebras and op-lax algebras, no, lax morphisms, yeah, just strict algebras and lax morphisms and op-lax morphisms, and that also fits into that. Okay, so but yeah.
Yeah, nice. I also liked it. Thank you.
Thank you.
there's any other questions, we still have a little bit of time.
I'm going to take this guy off the page that has 2 typos in it. Yeah.
I might have a small question, which is, you sort of gave the impression that the effective tabulators are the nice ones, and
Yes.
if a double category just has tabulators but they're not effective, then maybe I guess they're not as nice. But do you have some sort of intuition as to, you know, why tabulators might be nice even if they're not effective?
Well, so the tabulators are double limits. Okay, so you have double limits of you can talk about double limits. Okay, so you have functor categories, and then you can talk about the diagonal double functor, and you can talk about, let's say, right adjoint to it. That's double limit, and this right adjoint. I mean, so limits are clearly important, and tabulators are limits. Okay, so it's limit. It's a horizontal limit of the diagram, which is just one vertical arrow. So that's good. And something that I didn't mention is in the paper where Marco and I introduced these tabulators, we had this tetrahedron condition, which many people, you know, have told me they don't like and they have no use for. And we had put that in because tabulators are like comma categories. And the comma category has a universal property, and it also has the 2-dimensional universal property. And so we wanted a 2-dimensional universal property for the tabulators, and that's this tetrahedron condition. Okay, so the point of this is that tabulators are limits, and these limits might be lax functorial, lax normal functorial, or not. And this has nothing at all to do now with effective. Okay, it's just pure, and the normal part is this tetrahedron condition. Okay, so I mean, there's a whole other aspect of tabulators that I didn't mention here, you know, but I think that, you know, they are interesting, but it's certainly not sort of in the same spirit as what Freud had done at the beginning of trying to write a relation in terms of functions. Okay. So I do think that even if they're not effective, they're still good. Okay, I mean, well, there are limits. I mean, limits are limits, right? We like limits. We should.
Thank you.
Yeah.
Okay, well, if there's no other pressing questions, we might thank our speaker again.